In this video, I'm going to talk briefly about the theory behind the solution of second order linear homogeneous equation. Okay, so let us first start the theorem in which condition or what are the conditions needed for a second order linear differential equation to have a solution. Okay, so theory is let pt, qt and gt be continuous on an open interval I, and let t0 be any point in the interval I, and also let y sub 0 and y sub 1 are any given numbers. Then there exists a unique solution y equals to phi t of the differential equation y double prime plus pt y prime plus qt y equals to gt. See, so what is the condition that this equation, this second order linear equation have solution is this function and this function must be continuous in an open interval I, and if the initial time t sub 0 is any point in the interval I, then this equation has the unique solution in the interval I that satisfies this initial condition. Okay, that's the theorem. So basically what you need is you need pt, qt and gt to be continuous in the open interval I. Okay, so the next, instead of writing the whole equation, we want to use some notation for this. Okay, we call linear operator, second order linear operator. What you do here is basically this is like dy square over dt d square t, right? And so d square y over dt square, that's the second order derivative, right? And this one is dy over dt and so on. So instead of writing all these things out, let us denote d, uppercase d equals to d over dt, just the derivative. That's why dy will be dy over dt. Okay. Then the second order linear operator we denote by L equals to d square plus pd plus q. Look at this. This is like d square plus pd plus q, where this is equals to d square is the second derivative term plus p times d, uppercase d is first derivative plus q. Okay. Now if you use this notation, then the equation star becomes L and then y, meaning you are finding the second derivative of y, you're finding the first derivative of y, and then you multiply this q by y. So L, and then inside the bracket you write y equals to gt. That's what you are able to write there. Okay. And then also, so this is what we have. That's the same thing. Now if this equation is homogeneous, then the right hand side function gt will be 0, right? In that case, this equation, that operator equation, will be ly equals to 0. Okay, so this operator L will be linear. What does that mean? That means if y1 and y2 are twice continuously differentiable function in I, and c1 and c2 are constant, then this L can be distributed there. That means L of c1 y1 plus c2 y2 can be written as c1 L y1 plus c2 L y2. I forgot L there. c2 L y2. Okay, like this. Also another theorem here is if y1 and y2 are two solutions of this second order linear homogeneous equation, then y equals to, this is the linear combination, right? Y equals c1 y1 plus c2 y2 is also a solution for any c1 c2 constants. Okay, now so you remember that in chapter 3 we converted the second order differential equation into the system of first order equation, right? Let us talk about a little bit about that. Consider the system x prime equals to pt x vector x. That means x prime is x1 prime x2 prime. That's a vector form, right? And pt will have 4 elements, p11 p12 p21 p22 and so on. And then x is x1 x2. That is the system of two linear first order equations. You can write in the matrix form, right? Where the entries of pt, p11 p12 p2 and p22, all those are continuous on I, on the open interval I, and components of vector x are continuously differentiable. Let you denote that, if you bring this to the left side, you get k, and then denote that by kx. So let kx is x prime minus ptx. If you bring that everything on the left side, you will get x prime minus ptx. I denoted that by kx. In that case, then the operator k is linear. That means k c1x plus c2x, c1x1 plus c2x2 will be c1k x1 plus c2k x2. So this operator is also linear. Okay, guys. So what I'm going to do next is I'm going to remind you of the Wronskian from chapter 3. Okay, and and provide some results. Okay, guys. So let me remind you the Wronskian. So if vector u equals to u1, u2 and vector v equals to v1, v2 are the solution of the system x equals to pt times x, okay, then the Wronskian is the component of u and v, right? u1, u2 and v1, v2. That is the Wronskian. Okay, now let us consider, we want to find out what will be the Wronskian of this second order differential equation. That's what we want to do. So consider that y double prime plus py prime plus qy equals to 0, which is second order linear homogeneous equation. If y1 is the solution, then you can write y1 double prime plus py1 prime plus qy1 equals to 0, right? Now, how do I get the system for this? You get x1, you consider x1 equals to y1 and x2 equals to y1 prime, okay? Instead of y and y prime, we are just doing y1 and y1 prime because this equation has y1, right? So if you do that, then what is the system you get? System is x1 prime equals to x2 and x2 prime equals to negative qx1 minus px2, right? So on the matrix form, you can write vector x equals to pt times x. You see that? Where pt is equals to the matrix of the coefficient. So 0 and then 1, because it is 0 times x1 plus 1 times x2 and so on. And on the denominator, on the second equation, it will negative q times x1 minus p times x2. So this is what you get the matrix. Now, how would the solution of this equation, this system look like? It will look like x1, x2, right? Because the solution of first one will be x1, solution of the second will be x2. Now, so x1, x2, but what is x1? x1 is y1. And what is x2? x2 is y1 prime. So basically the solution x1, x2 will be y1, y1 prime. Okay, so the solution of this system, which is the same as the solution of this system, this second order linear homogeneous equation, right? So the solution, the first solution look like y1, y1 prime. Similarly, if you take y2 as another solution, you will get the solution vector for the system will be y2, y2 prime. Okay, so now what will be the Wronskian in this case? Then Wronskian for this second order linear homogeneous equation will be w, and then you always denote by y1 comma y2 inside the bracket, right? Just the solution and then bracket, and which is the determinant y1, y1 prime, which is the first solution, this one, right? And then y2, y2 prime is the second solution. You see that? So this is the Wronskian in case of the second order linear homogeneous equation. Okay, and also recall that if the Wronskian is not 0, then we call y1 and y2 as the fundamental set of solution, right? So if Wronskian is not 0, then y1, y2 are the fundamental set of solution, and in that case the general solution is y equals to c1 y1 plus c2 y2. So basically this is the linear combination of those two solutions. Okay, guys. Okay, so this is how we can relate the Wronskian of the system to the Wronskian of the single second order linear homogeneous equation. Okay, guys. Now, so I'm going to give you a theorem, statement of the theorem. If you want to see the proof, then you can basically look at the book. It's just a short proof. Okay, I'm going to give you a theorem that tells you that there is an alternative way to find out the Wronskian of a second order linear homogeneous equation. Okay, that theorem is called Aval's theorem. So let us look at the Aval's theorem for the pair of equation or the system of first order linear ODE. The Wronskian of the two solutions of x prime equals to p times x, pt times x is Wronskian equals to c times e to the integral p11 plus p22 dt. What is p though? P is basically p11 p and then 21 and then p12 p22. That is the vector p. Okay, that is vector p. So p is that. So if you want to find the Wronskian of the system of equations directly, what you do is you do c times e to the this plus that. Okay, integral of this plus that and dt, and you find out the integral, and whatever you find is the final answer, where c is the constant here. So the next thing is, so this is for the system or the pair of ODEs, right? Linear ODE. But if you have a single ODE of this form, second order linear homogeneous ODE, how do you find out the Wronskian? Is basically WT equals to C times e to the negative and then that thing, negative PT dt, right? It is kind of similar to the integrating factor kind of, right? But see, integrating factor was for the first order linear ODE, but this is second order linear ODE. So C times e to the negative integral PT dt, whatever you get here, and you do dt, where C is a constant. Usually to find out C, you find out C at the Wronskian at t0, right? C is equals to Wronskian at t0, which is same as W at y10 and y20. Okay. So let us look at the very last theorem of this section. If y1 and y2 are two solutions for the equation y double prime plus pty prime plus qty equals 0, where p and q are continuous on I, then the Wronskian is either never 0 or always 0 for all values of t. That's what it is saying, okay? So the this W, so the Wronskian W is either never 0 or always 0. That's what you get there, okay? So let us do some examples, then things will get clear. Let us do the first example. Find the largest interval in which the solution to 2t square plus 2t square y double prime plus ty prime minus 3y is equals to 0. Okay, that's what you want to do here. So how do I find out the largest interval there? Is basically, do you remember that? How do I know what is the theorem behind the existence of the solution, existence and uniqueness of the solution of this equation is? So we need to find out P and Q, and then P and Q must be continuous, right? How do you write that? You can write this equation. Let me write down solution is y double prime plus t over 2t square, right? And then y prime minus 3 over 2t square y equals to 0. That's given, right? And t0 equals to 1. So what is the point of discontinuity? So t equals to 0 is the point of discontinuity. So this function pt, this is pt, right? This function is pt and this one is qt, right? With negative sign. So pt and qt are continuous everywhere except t equals 0. After you cancel that t with that t, there is one t left, right? So except t equals to 0. Now, which is the longest interval that includes that initial value? The initial value t0, the initial time is t0, right? That t0 lies on which side? That lies on infinity. You see that? That lies on the infinity. So what do you get then? So since this since the function pt and qt are not continuous at 0, then the possible interval will be either 0 to infinity or negative infinity to 0, right? But where does this value belong? t0 equals to 1 belong on this. So the answer is 0 to infinity, right? Next is you want to find out what? You want to find out the Wronskian, right? What is the formula to find out the Wronskian? Wronskian is c times e to the, what is the formula there? E to the negative and then pt dt, right? Integral pt is what? 1 over twice t? 1 over twice t dt. You see that? So what do you get there? So you get c times, let me write wt there. So wt is c times e to the negative 1/2, and then integral of 1 over t will be natural log of t, right? dt. So that you don't need dt. So how can you write that? C e to the, you can write natural log of root t, right? To the negative 1. So how that look like? That looks like, it looks like e to the natural log of 1 over root t. Why 1 over? Because if you move this negative 1/2 here, you will get t to the negative 1/2, right? T to the negative 1/2 will be 1 over t to the 1/2. So it is like, it looks like e to the natural log of t to the negative 1/2. That's what you get. And this is same as 1 over t to the positive 1/2 there, right? So which is root t. So 1 over root t you get. C e to the 1 over root t. But this exponential and natural log cancel out. So you get c times 1 over root t. Oh, by the, yeah, c times 1 over root t. That's what you get, right? So that is basically what? That is basically c over root t. That is the Wronskian for this problem. Okay. All right. So let us do another example. Find the largest interval in which this equation has a unique equilibrium. So let us write down in the standard form. So you get y double prime minus 2x over 1 minus x squared, and then y prime, y prime is in the top, right? So y prime, okay, plus alpha times alpha plus 1 plus mu square divided by 1 minus x square, and then y equals to 0. Okay, so what is the value of t0? T0 is the beginning value is basically 0, right? So where is f and sorry p and q, what is the interval that p and q is continuous, or find the point where p and q are not continuous, right? So pt and qt, what is pt? Pt is that value, right? You see that pt is this value and qt is this value. So pt and qt are continuous except x equals to plus 1 and minus 1. Okay, so what are the possible interval? Negative infinity to negative 1, and then another possible interval is negative 1 to 1, and another possible interval is 1 through infinity. You see that? So which interval contains the initial value? That is, initial value is t0 equals to 0. So which interval contains 0? So negative 1 to 1. So hence the unique solution exists. Unique solution exists in the interval negative 1 to 1, right? So the unique solution exists in the interval negative 1 to 1. Negative 1 to 1, or you can write negative 1 is less than x is less than positive 1. So this is how you find out the interval where the unique solution exists. So let me remind you what we just did before. So what we said is, if y1 and y2 are the two solutions of the second order linear homogeneous equation, then the Wronskian of those two solutions y1 comma y2 is equals to y1 prime and then y2 prime. Okay, because previously we used to have a system of two linear first order ODEs, and then each of the solution had two components, right? X1, X2, and then another also has like U1, U2, like that, right? Two solutions, and our Wronskian was X1, X2, U1, U2, that way, right? But here you have just only one equation, so y double prime plus py prime plus qy equals to 0, right? So in this case, each solution do not have two components, but although we when you solve it, you try to change that into the pair of two first order linear ODEs, but without doing that, we can also find out the Wronskian. The idea is the solutions and its derivative, another solution and its derivative, and find the determinant of that. Okay, so let us do an example. Find Wronskian if the solutions are et sine t and et cosine t. So what is the derivative of this? So the derivative of this will be e to the t cosine t, right? And then plus e to the t sine t. And how about the derivative of this one? This one will be e to the t negative e to the t sine t, and then plus e to the t cosine of t. That's the derivative, right? So what is the Wronskian here? Wronskian will be determinant of e to the t sine t. It is like y1, and the derivative is e to the t cosine t plus sine t. I can take that e to the t out. Similarly here, e to the t cosine t, right? And then here it is negative e to the t sine t plus cosine of t. So you can write let me write down here like this. So what I want to do here, is I want to take e to the t out, and then I want to write cosine of t minus sine t, and this is the determinant. Okay, so what we want to do here to find out that is basically, so let me write the w y1 y2. Okay, so Wronskian of y1 y2, or you can write this that way, that's not a problem. Now the determinant, so e to the t times that, it will be e to the twice t times sine t cosine t, right? And then minus e to the twice t times sine square t, right? And then this times this will be negative multiplication, right? This will be negative multiplication. So it will be minus e to the twice t cosine square t, and then minus e to the twice t sine t cosine t times cosine t. So this e to the sine t cosine t, this one plus and minus cancel out. So what is left is, let me pick negative e to the twice t out. You get sine square t plus cosine square t. That is 1, right? So it will be negative e to the twice t. This is what you get. So so the Wronskian is negative e to the twice t. Okay, now let us see another example. So can y double prime plus pt times y prime, okay, plus qty equals to 0 with p and q continuous have solution y equals to sine t square as a solution on an interval containing 0 or not? That's what it is asking. So what we need to do is we need to plug in this into here and then test if you get left side and right side equal or not. Okay, so what is the derivative of y here? So the first derivative will be, so cosine t square, right, times twice t. That's the first derivative, right? What is the second derivative? Second derivative will be the product rule on this, right? So it will be 2 cosine t square, right? And it will be the derivative of, so it will be minus twice t, y minus, because the derivative of cosine will be sine, right? So sine t square times twice t, because the derivative of inside, right, the chain rule. So 2 cosine t square, you see that, and then minus 4t square, right, and then sine t square. That is the second derivative. Okay, now so let us plug in here. So if you plug in, what do you get? If you plug in that, you get y double prime is negative 4t square sine t square. I'm just putting t square term at the beginning, right? That is, and then plus 2 cosine t square, and then plus pt times y prime. Y prime is 2t cosine t square, right? That is y prime. Pt times y prime plus qt times sine t square equals to 0. So if you plug in t equals to 0, do you get left side and right side equal or not? Okay, that's what we want to do. So let us see that. So if you plug in t equals to 0, then you get when t is equals to 0, what do you get on the left side? It will be, that will be 0, whole thing will be 0. That will be positive 2, right? That will be cos 2t. So this whole thing will be 0 because 2 times 0 and anything multiplied to 0 is 0, and this is also 0. So you get 2 equals to 0. 2 equals to 0, which is false. So that this equation cannot have this as a solution in any interval containing 0. So the answer is no. That's what we can say. Okay, guys. All right. The last example on this section 4.2 is so that y1 and y2, these values, are solution of this equation. We will plug in here. We will plug in this one here and then find out that. Okay. And do they form fundamental set of solution? How do I know that the two solutions make a fundamental set of solution? Is basically you check the Wronskian, right? If the Wronskian is 0, then they are not the fundamental set of solution. If the Wronskian is not 0, then they make the fundamental set of solution. Okay, so let us try that. So for y1 equals to e to the t, and y1 prime will be e to the t as well, and y1 double prime is equals to e to the t as well. So what is y2? Y2 is t times e to the t, right? What is y2 prime? Is a product rule, right? So t e to the t plus just e to the t. That is the product rule. And so you can write this as t plus 1 e to the t, right? So what is y2 double prime? Y2 double prime is, you can write t plus 1 times e to the t plus e to the t, e to just e to the t. So if you factor that e to the t out, e to the t, you can write t plus 2. So this t is on the exponent, okay, e to the t. So let us see for each of those solutions. I want to check if they satisfy the this equation. So this one is e to the t minus 2. I'm just checking for y1, okay. 2 times e to the t plus e to the t equals to 0. So see, e to the t plus e to the t is 2 e to the t minus 2 e to the t equals to 0. So 0 equals to 0. That is done, right? So next one is plug in those things, okay. So plug in that. So t plus 2 times e to the t, right? And then minus 2 times t plus 1 e to the t. T plus 1 times e to the t, and then plus t e to the t e to the t. That is y2 double prime minus 2 y2 prime, right? And plus y equals to 0, right? So let us see that. If you take e to the t out, what do you get? E to the t out, t plus 2 minus twice t minus 2 plus t. You see that? That t and that 2 and 2 cancel out, right? 2 and 2 cancel out. So twice t, t plus t is twice t minus twice t is 0. So 0 equals to 0. That's what you get. Okay. Now both of them satisfy the solution. Now we want to check if this solution, if they have, if they are the fundamental set of solution or not. Okay. So how do we find out? For the fundamental solution check, we need to do the Wronskian. Okay. Wronskian is equals to, so e to the t, that is first solution. Another solution is t e to the t, right? So what is the derivative of e to the t? E to the t itself, and derivative of that is t plus 1 e to the t. That's what we got the derivative, right? Find out that. So you multiply that one, and the other multiplication is negative multiplication, right? So you write e to the twice t, t plus 1, right? And then minus t e to the twice t. So what do you get? If you simplify this, if you distribute these to t and 1, you will get t e to the twice t, and but there is a negative t e to the twice t, so that will cancel out. So only what is left is e to the twice t. So the answer is, it is not 0, right? So hence they make a fundamental set of solution. So the answer is yes. Yes, they are fundamental solution. Fundamental set of solutions. That's what we get. Okay, guys. Thank you.